So let us start. So in the last lecture, we talked about score-based models, or rather, we started talking about score-based model. Today, we will continue with score-based model. Hopefully, that will transition into diffusion towards the end of today's lecture. But we will not talk about diffusion in details. I'll probably just give you the intuition how score-based model becomes diffusion, and that's where we will kind of stop today. And then tomorrow, same time, there is a lecture. Tomorrow is Friday's schedule. So that will be here only. Okay. Same time. Monday, practical will not take place. Instead of that, lecture will take place. The lecture time will be 3:30 to 5. The venue is LH 510. For Monday, I will send an email because that is different. For tomorrow, it's Friday, so I'll not send an email. I mean, it's supposed to be there. It's the same location, same time, so I'll not send an email for tomorrow. But for Monday, I will send an email. Although I booked the room already. So that will take place in LH 510, if I'm not wrong. Okay. And obviously, after that, so yeah, so basically, starting tomorrow, we'll talk about diffusion only. Today, we will look into a transition of from score-based model to diffusion, probably towards the end of the lecture, right? Okay, but we'll start with review. We'll start with review of everything we did in the last lecture, because whatever we discussed today is a follow-up from what we did. So if you remember, I mean, we were talking about score-based model, right? Score-based models. And the idea in score-based models is that you train or you have a scored network, a network that takes the image or input and gives you score. So the idea is you have a S theta, which is the scored network, which takes X, which is your training data or data in general as input, and will give you some score, right? And then we will somehow try to use this scored network to generate samples. First, we will train this scored network and then use it for generating samples. We talked about two ways of doing this, but fundamentally, how will you train this model is exactly same as energy-based model. So we train score-based model using Fisher divergence, right? Fisher's divergence. We train score-based model with Fisher's divergence, which is f of theta is equal to half expectation with respect to the data distribution and the norm of grad x log of px x minus s theta x. That's it, right? But we cannot use it. We don't use it. So what we use, and again, nothing new, so I'm going a little fast because it's a review. What we use is if maybe tilde theta is equal to expectation x from px and then half norm of s theta x plus trace of grad x of s theta x, something like this, right? This is what we use, right? Nothing new. What is the problem with this? That gradient computation is expensive. I mean, you need d passes if d is the number of dimension. We discussed about that. Or if you don't want to do deep passes, then the cost is memory, which is maybe million cross million. So basically this is not scalable. So we talked about how to make it scalable, and we talked about two schemes. What were the two schemes? Denoising score matching and sliced or slicing score matching, right? We talked about that. So it's not scalable. And what we talked about is denoising score based model or denoising score matching and sliced score matching. Okay, I'm not writing the full name, nothing new. Right, these are two things we talked about. In denoising score matching, what was the idea? And this is what we will be focusing on more today. We will not focus on the other one, but in general, what was the idea? That instead of the actual data, you work with some noisy version of the data. You add some small noise to the data, and then you train based on that. And we saw that when you train based on that, what the network tries to learn is the noise or some scaled noise. That's what we saw, right? So we are not planning to train the network to denoise, but it is learning somehow the noise part. I mean, it is happening because of the formulation. We are not forcing anything, right? So denoising score matching. Here the loss function is, let's say, what was it? F, right? So let's write like this. So this is equal to 1 by 2 expectation x from pxx. And here what you do is you have the norm of grad of x log of q x, or I can write q sigma x, let's say, minus s theta of x. So instead of matching from this, we try to match from the noisy version of that, right? X tilde comes not in this form, x tilde comes in the other form. But this, again, we don't use this form. What we do is we write it in terms of the conditional distribution and all of those things. And when you write it in terms of the conditional and all of those things, this kind of reduces to half expectation. You have x from pxx, x tilde from q of x prime given x, something like this, right? And then inside, what do you have? You have x minus x prime, so which is basically that log of whatever that is, right? So let me write that x minus x prime by sigma square minus s theta of x prime norm of that, right? Something like this, right? I mean, again, to make it generalized, you need not write this part. You can also write it as grad of x log of q x tilde given x. I mean, that's what it is actually, right? That's the term. X prime.
The log of q sigma.
Q sigma. So what is sigma? Sigma is a noise variance. So x prime is equal to x plus some noise. So that noise has a variance which is very small. We should decide that, and that is sigma. Last time I did not wrote it as q sigma. I'm writing it today because you will realize why. So that sigma will have a role to play later. So this is what we did. This is fast. This is fast because there is no gradient in the loss function. And that is why it is fast. And we talked about it, right? The other thing also, let me write it down for completeness, was slicing or sliced score matching. And here what we do is that we project into a one-dimensional axis and compute there. and that projection changes every time. And the hope is that because it changes every time, we ultimately calculate the correct thing. So what is the loss function in this case? So f, let's say theta is equal to expectation, and I'm now writing the total thing together. You have v from some p of v, you have x from the data distribution, and inside you have half, and then v transpose s theta x square of that plus the second term is v transpose gradient with respect to x log of px, not log of s theta, sorry, grad of s theta, not log, sorry, right. S theta v. Okay. This derivation I did not do, but it is very similar to the derivation we did earlier, which is basically you do integration by parts and you arrive at this. And we discussed why is it useful. And this is where we stopped last time. No, actually, this is not where we stopped. We also talked about sampling. We also talked about sampling last time. And in sampling, again, there was nothing new. We are using Langevin Monte Carlo or Langevin dynamics unadjusted. And from there we are sampling. So let me write that as well before we start something new. But we will refer to all of these things I wrote today till now because that is needed. So sampling, how do you do it? It's simple. X t plus 1 is equal to x t plus eta times the score basically. So let's write s theta x t plus square root of 2 eta epsilon, where epsilon is from a Gaussian 0 comma I, where I is equal to the number of the dimension of x. Like each pixel you should add noise in that sense, right? Okay. These are all the things we discussed last time, right? So now, today, let us start by comparing, although I slightly compared them, the slicing score matching and the denoising score matching. So if we compare between these two, which can you tell me what are the pros and cons? So let's talk about the pros. What are the advantages of denoising score matching in your opinion as opposed to slicing score matching? What is the advantage you think there is? We don't need to find gradient. Here, yes, it is only a single backward pass, but it's still a single backward pass. In denoising score matching, there is no backward pass. Exactly. The pros, if we look it from the denoising score matching perspective, the pros in favor of that is that it is efficient. It is more efficient as opposed to slicing. Now, what is the con? Not true, but you are in the right direction. So what? So that gradient you cannot use here. You have to still evaluate it because x has changed. That does not help. Because you will now do it for a new sample. xt will change. Con, so pro advantage of, let's say, of this slicing. What is the advantage? You don't have to do 2 times back propagation. No, you opposed to denoising. I mean, I am comparing these two. What do you think can be the potential advantage of slicing score matching? First of all, it is more accurate. It is more accurate because look at how you are computing this sampling, and that's why I said he is in the right direction, right? Look at how you're doing the sampling. For sampling, you need the score. You need the score of the true distribution. But here, what do you have in that case? You have the score, but you have a score of some noisy distribution. So that means here the score term is changing when you will sample, which means it is little bit, at least little bit less accurate. Because you will ultimately sample using this thing, right? At least till now. I have not discussed anything else, so we'll sample using this. If you're sampling using this, for accurately sampling it, you need S theta to be accurate, right? But in that case, you are getting the S theta you are getting is with respect to Q and not with respect to Px. That means this S theta is not accurate, correct? Because the S theta is not accurate, the samples you get might be noisy or might not be so, might not be so good, right? Optimize that thing with respect to Q, not with respect to P. We do all the calculation, but with respect to Q. That's the thing. Clear? Advantage is, and I'm talking from a denoising score matching perspective because that's what we'll be discussing. Advantage is it is fast. Disadvantage is we have changed the goalpost. We have changed our target. We are now working with Q sigma and not with P. That's the disadvantage. In general, forget about this, we'll come to this later. In general, with score matching, what do you think are the challenges? Can you think of challenges in score matching? Not with either of this, in general score matching. Challenges with score matching or score based model. Whatever I have written till now should be enough. So you don't need to go back too much. Just look at everything I have reviewed and from there you should be able to answer. In fact, I'm talking about the generic one, remember, keep that in mind. Not denoising, not slicing, but the generic one. And I'm assuming I have infinite computational resources, so I can do everything perfectly. So not from a computational point of view, but from an accuracy point of view, from the sample generation point of view, can you think of challenges? So I'll repeat. Can you think of challenges of score-based models? Not from a computational point of view, but from an accuracy point of view, or maybe from a theoretical point of view when it will fail. So what do we do in score matching? Map, right? And then how do we sample from score matching? Langevin dynamics, right? And Langevin dynamics has a term called score. How do you calculate score? Gradient of log of probability. Hold that thought. Hold that thought, right? Now let us go to the motivation of VAE. What was the motivation of VAE? VAE, not GAN. That latent variable. Any high dimensional data we have, actually not everything is independent. It actually resides on a low dimensional manifold. So if you take a PCA of that, for example, you will see that even if you discard most of the things, you will be able to reconstruct the image. Right? So any or most at least high dimensional data resides in a low dimensional manifold. Like for the human face, remember eyes, nose, hair color, all those things we talked about. Correct? Because it resides in the low dimensional manifold, what does it mean to reside in a low dimensional manifold? It low rank, that is correct, but I've already used low dimensional, so that's you are repeating. So anything beyond what I've said. Residing in low dimensional manifold means as long as you are on that manifold, you will have a finite probability mass. The moment you go outside that manifold, the probability of that point will be 0. You agree? If something is residing on a manifold, as long as you are on that manifold, you will get a finite probability. If you go outside that, it means that will be zero. It is similar to saying what is the probability of mass being negative. Similar thing. I mean, mass will never be negative. So mass less than negative, the probability of that is zero. You agree? Now, in manifold, do you know in which direction we move? Tangential direction. Correct? In manifold, we move in a tangential direction. What happens even if you move by a small amount in the tangential direction on a manifold? You move out of the manifold. So what will that probability be? Zero, right? So there will be many points whose probability will be zero, unless and until you somehow is guaranteeing that it will always be in that manifold by some manipulation or something like that, right? What happens if your probability is equal to zero? Log of zero is minus infinite. So what is the score of this thing? Gradient of log of probability. It will be non-existent, right? It's undefined in every sense actually, which means your score-based models will fail.
So we can add some kind of epsilon value into that so that it should not go to zero.
But then that is not the original score-based model. If you add that, you are violating the original score-based model. The question was theoretically where will score-based model fail? That's a numerical manipulation you are doing, but that's not really score-based model then. Then you are doing some denoising basically. We did denoising, right? And you can imagine that with denoising this problem will not be there. But with score-based model, you can imagine that in high dimensional images or time series, whatever, if it resides in a low dimensional manifold, which is almost always the case, you will get many points where the score or the probability will be zero, which means you will have no additional information that you will get from there. So that term will add nothing, right? That is one of the problem that we have, right? Gradient, you move radially. The score is defined so that the vector field is towards the maximum, right? But score at that point is the gradient of something that is zero at that point, minus infinite at that point. Okay. So it will become problematic to handle, obviously. Any other problem you can think of apart from this? Apart from this, there is one more problem. This problem, the solution is not a solution. The observation is mostly empirical. I mean, this one, what I said just now, I can prove it if I want, right? If I take a manifold, I can show you that what will happen in that manifold, right? But what I'm going to tell now, I cannot prove it mathematically, but this is more of an observation. When you train based on the original score, with iteration and updates, the behavior is quite erratic. You will not have this kind of behavior that you expect with epochs and whatever, right? It will be something like a noise or something like that. So training the model is very difficult with score. That is the second challenge. There is probably more challenges, but I think for now, these two should be enough to motivate you for what I'm going to talk, right? So challenges first is low dimensional manifold. I'm not writing in details, but it means that if the data that the distribution of the data we are trying to learn, if that resides in a low dimensional manifold, then score-based models will struggle. When I write low dimensional manifold, that is what I mean. If you want, you can write it. I'm not writing it, but I hope that is clear. The second one I said is training is erratic, unstable, maybe unstable is a more scientific term. There is one more issue, but that will not be solved by what we're talking about now. But because of this use of Langevin thing, you train to sample more from the modes, because that score takes you towards the modes, and low probability area you have a high chance of missing out. And that happens because of this Langevin dynamics thing, right? Because remember, as Aryan was saying, that the score points towards the modes. So basically, because of that vector field, it will try to take you towards the modes. And if it takes you towards the modes, that means most of the samples will start coming from the modes. But there are other areas which are probably not modes, but have non-zero probability. Those areas getting samples become difficult.
Lowest extreme actually.
Lowest extreme is okay, but even mid kind of area, even there. Yeah. So most samples will start coming from the two modes. You also want samples from other places, right? That's what learning the distribution means. Yeah. You need not be. Depends on the manifold. How does it look? Yeah. So it depends how you look. I mean, when I'm saying it resides on a manifold, it's on the surface. I'm saying, not inside. I understand what you're saying. You are thinking like a tube, right? Probably. I'm saying in the surface. So in that sense. Okay. So that is the issue that happens here. So now, interestingly, the solution to both of this is adding noise to your data. So denoising, score matching, what we did is the solution for both of this. But it has its own challenges. We'll discuss about that more. But why is it a solution? Again, as I said, the second one is empirical. It has been seen that by adding noise, the training stabilizes. That is empirical. The first one is obvious, because you are adding noise. Because of that noise, all points, even where previously the chances of the point being 0 will now have some finite probability. The probability can be small, but it will start having some finite probability. So the solution to both of this is adding noise to your data. Okay. So for both of this, the solution is adding noise. When you add noise, whatever points were 0 probability, because of that noise will now have some small probability. And the second one, again, I said it's empirical. It has been seen adding noise kind of acts as a regularizer. Last time I used that terminology. And that allows you to get the kind of convergence you're looking at. And interestingly, the more the noise, the better the behavior. So the more noise you add, obviously the other points will have the probability mass will increase. The points that were having 0 probability, if you add more noise, the chances of having 0 probability will increase and will be higher, obvious. So first problem, the more the noise, the better it is. Second one, training is unstable. Again, the more noise you had, it kinds of stabilizes more. So both of this, adding noise is the solution. And interestingly, more the noise, better the stability or whatever you call it, right? But that is the problem. Because if I add too much noise, I can estimate this Q of sigma or whatever, but that will be a wrong estimate. Which means, yes, I can find that very easily, but what I'm finding out is actually wrong. Because I have changed my target itself. Which means the samples I will get will be just noise. Right? So, what I said, let me write it down because this is important, very important actually in this context. So first is more noise leads to better estimate. Okay. More noise leads to better estimate. Okay. But this also leads to wrong target. So you are getting a better estimate, but you are getting a better estimate of a wrong target. If noise is 0, then I'm not getting a better estimate, but that's the accurate one, log of px. When I add a small noise, my estimate for log of sigma, grad of log of sigma improves, but that sigma is with a very small noise. So it improves, but it's not that good. If I add even more noise, my estimate is very good, but that log of sigma, whatever I have, is total noise. Right? So what is happening is, if there is no noise, I cannot estimate, almost. I can estimate, but almost I cannot estimate. If I add a small noise, the difficulty reduces from no noise, but I'm estimating something wrong. My target is wrong. And as I keep on increasing noise, my estimate becomes better and better, but I am estimating something wrong. Clear what is happening? And to understand that, go to here. That expression. Look at the first expression. Log of q sigma, right? It should have been px. I got q sigma instead of px because I added that sigma. Now, if that sigma value is 0, that means I have px. In that case, it is the most difficult to estimate. If sigma equal to sigma 1, which is a very small noise, then estimating theta is easier than when sigma equal to 0. When for sigma 2, it is even easier. But as I keep on increasing this noise, estimating theta is becoming easier and easier. But what I'm estimating log of q sigma is becoming wrong and wrong. Everyone follows what is happening here? And that is a problem, obvious problem, right? We need solution for that. And to find the solution, I think the first thing that we should ask is, yes, there is denoising chord matching, but what is the noise that I should add? Last time I said very small noise, but now you know that very small noise means the training might not be that stable. You might want to add more noise to make it more stable. But if you added more noise, then the training is stable, but what you are estimating is wrong. Estimation is correct, but what you are estimating is, the target is wrong. So what is a good sigma here? What is a good sigma for denoising score matching? Right? We need to answer this question, and the answer to this question need not be simple. Okay. So the question is, what is a good sigma? Okay. What is a good sigma? Now think about how this sampling works, right? As I said, I will refer to this again and again. And that's why I took 10 minutes to just review everything. How does the sampling works? What will be x0? What will be x0? T equal to 0. Because you have to start from something, it's autoregressive. What will be x0? It will be noise. Monte Carlo starts with noise or some initial estimate. And the idea is, if you let the chain run for long enough, initials will be burn-in period, and after that what you get is the sample. Right? So initial is anything, but it's something random. Right? So xt is random. Correct? And then what is S theta doing here? What is the role of S theta? No, in the sampling, what is it doing? It is trying to move those samples you have generated towards the mode. Right? It is trying to move the samples towards the mode. And epsilon at the end is for exploration, so that you just don't get the mode, get some samples around the mode. Epsilon is for that. Right? So initially, what do you think S theta, if S theta is wrong, is that a problem initially? Or it is again, wrong means sigma. So remember, when I say S theta, you should think of it like sigma also there. So a small, initially should you have a smaller sigma or a larger sigma? Larger. It's okay, let it explore and initially. So initially you can have a larger sigma. But with larger sigma, what will happen? The samples will start moving towards the mode in some noisy manner. Now they are near the mode. At that point, what should you do? The sigma should be smaller so that it can converge to the mode. Which means the idea I'm giving is about annealing. Annealing sampling, or this is known as annealing, which is done in sequential Monte Carlo, or annealing sampling is also the term for that. Particle filter is another name for that. Where the idea is, initially you sample from something different and then slowly annihilate, slowly make the sigma smaller and smaller and smaller, so that ultimately the final step, the samples you are getting is from the target distribution. So initially you will use S theta, which probably approximates Q of sigma n. And then slowly, at the end, you will have S theta that represents Q of sigma naught, which is Px of x. Or maybe not Px of x, but a very small sigma. Right? This sounds logical?
Sigma at the initial level. As there, obviously exploration is possible, but also can go to some another direction also, that is also possible.
Unlikely. Large does not mean infinite. Large means that large has to be bounded by something. You should not take such a sigma that the data points, because it is x prime is equal to x plus sigma. You should not take such a x plus epsilon. You should not take such a sigma that epsilon dominates and your x tilde is something like only noise. We will have to take. We are not yet taking. But the question is, how will you take? And we will have to take something, and that range will come from some, the lower range is kind of obvious. It should be very small. But the higher range, how to decide, we'll have to discuss that, and we will discuss that. Right? But obviously there has to be some range. It cannot be that you take as high as possible, because then it's only noise. Then, so what will happen? That's a interesting, let me see. What do you think will happen if I take sigma to be very large?
May miss the stationary distribution.
Think about it. What will happen if I take sigma very large? I'll have only noise, right? It will, so S theta will correspond to the noise distribution. That means whatever initial sample you draw, it will be like drawing sample from the same initial distribution. It is at the noise. It will just generate samples for noise. It will be, yeah, Gaussian, right? Gaussian noise. So if you take sigma to be very large, that means it's basically learning score of a noise. If you learn score of a noise, this will let you sample from a noise. So you will sample noise at that stage. So sigma has to have some bound, obviously, and that will come from some logic. But assuming we are in a reasonable bound, does it make sense that initially we'll use large sigma to allow exploration? It's similar to taking large eta in optimization and later taking a small eta. Same kind of concept. Initially take a large sigma and then slowly tune that sigma to very small, not zero, but very small. Yeah.
Sigma related to exploration. From what I understand, that exploration should be controlled by that eta.
Correct.
And that score thing is matching, looking to find the difference between the noise and our original ground fields. So sigma is the
Scaling term.
difference scale between
Scaling term. X minus x prime by sigma square is equal to score, right? So score, so that is the scaling term. Think about how will it happen. So where is that? Here. Q of sigma and S, right? When you add large amount of noise, Q sigma will, what will happen? It will be x tilde or x prime is equal to x plus epsilon. That epsilon will be very large. So x will happen, whatever x is there, it will enlarge. So if the mode was this kind, it will become this kind of thing. It will still take you towards mode, but not towards this mode, towards the bigger mode. So it's not, you are right, it's not purely exploration, but there is some sense of exploration there, right? Because what is 1 will become 1.5 now. If the radius was 1, it has become 1.5. So in that sense. But you are right, the second term is purely exploration, the epsilon term. But here also there is some sense of exploration balance in the sense that you are enlarging those parts.
Is also like learning rate only.
Learning rate. Yeah.
Yeah. So that learning rate itself also goes this kind of behavior. How will we trade off this?
Learning rate, generally there is some constant and we take it. We then use that to do this thing.
Also,
Yeah, warm up is fine, but that has nothing to do with this eta. Warm up will anyways be there. The burn-in period you are talking about, that will always be there, but that has nothing to do with eta actually. Because here you have to keep in mind that here we are doing this thing because we want to use good estimates of S theta and accurate S theta together. Not accurate S theta, but accurate score. We want some trade-off between good estimate of score and accurate score. Now, good estimate of scores are the wrong scores, and accurate scores are the bad estimates of the score. We want some balance between those. So that's why we are doing this.
So all this will happen in the sampling part, not in the training phase.
For doing this in the sampling part, we need to do some changes in the training part, but right now, yes, in the sampling part. Because, for example, how do you have a score that can handle different sigma? So, will you train 1,000 different score networks? So, some changes have to happen in the training part, as you can probably foresee. But right now, I'm only discussing the training inference part, or the sampling part, because that's the objective. And for achieving that objective, whatever needs to be changed in training part, we'll do that.
So you have mentioned the training is stable, and this is really helping in the training also.
This is not happening in training.
This is not happening, but you said adding noise.
That's helping. Correct. Correct. It will come there, right? It will. We have to reach that point at some stage. Okay. Any question? Okay. Okay. So what is a good sigma? We do not know. But what we are trying to motivate is, can we do some kind of annealing so that we use larger sigma at the beginning and smaller sigma at the end? I think that is the part we agree on. And let's move on from that. So, can we use annealing? This means large sigma at the start and then reduce it gradually with chain length. Right? This is similar to multi-scale sampling. You are sampling for different sigma, different distribution. So this can be thought of as multi-scale kind of sampling, where you are you're sampling at different scales, but scales being sigma. I mean, sigma is anyways a scale, right? Scale and shift, meaning is the shift, sigma is the scale. So in that sense, this is like your scale sampling at different scales. Okay. So what will you do? You will first use larger sigma and then smaller sigma. But in what range the sigma should vary, and how should you select sigma? What should be the number of steps? What should be the number of sigmas you should use? These are now hyperparameters in your model, right? So range for sigma. Any idea? Any idea how can you find range? Again, not mathematical, but some common sense kind of answer I'm looking at. No, in this case, what range? So I'm now lower range should be very small. I'm only talking about the upper bound. So not how many sigma, what would be the maximum sigma? It will depend on the problem. So not numerically. Numerically cannot tell. So it will depend on the problem. So using the problem, can you think of something? Maybe let me help you. When you talk about a problem, what do you have in a generative model problem? Data. That's all you have. That means this sigma needs to be function of the data, right? So now as a function of data, can you think of something? You don't know the data distribution. If you know the data distribution, then we don't need this course, right? Oh, you don't know the data, that is correct. Okay. So when you said you don't know the data distribution, I remember that in it's 3-2, right? He's when he said that circuit का सर नहीं है, like इसके लिए IS दे दो, so that's what I felt. Right? So, anyway, so how could you decide sigma? How? Yes, that is the right way of thinking. So one of the ways you calculate pairwise distance between the samples, and the idea is starting from any sample you should be able to reach any other sample. So whatever is the maximum you get pairwise distance, that's your sigma max. A very common sense kind of answer, nothing mathematical again, but the idea is that you from your training set you calculate the distance between all pairs and the maximum of that. This basically says in the training set at least starting from any sample with this sigma you can go to any other sample, right? So that's one way. There can be other ways also. You can read the literature, but this is the way we are going with. Okay. So sigma max is basically maximum pairwise distance maximum in training set. Okay. Why should it be computational? To calculate the distance, there are 100 algorithms to find the pairwise distance. There are at least 100 algorithms that rely on pairwise distance, starting from graph neural network in deep learning to SPH, mesh-free method, MPM, molecular dynamics. I can talk about many more. So there are algorithms that can do that. So if you do it in a brute force manner, it's expensive, no doubt about it. Okay. And this will allow starting from any sample, you can jump to any other sample and to and fro. Basically, you can at least sample everything, no matter where you are. Remember the properties of irreducibility in Markov chain? This kind of guarantees that, at least in the training sets. From here, you can go anywhere, any state to any state, the same thing, right? Okay, clear? What is sigma mean? As small as possible. Okay, not 0, but very small, maybe 10 to the minus 3, minus 4, minus 5. You don't take the only nearest point here. It can be even smaller than that. They can be independent also, and because mean, right? Sigma mean is as small as possible. Okay, so basically this you will decide based on whether you are able to train or not, in some sense. Now, how will you schedule the sigmas? Not how many sigma, but how should you schedule the sigma? Okay, the sigmas should be scheduled in such a manner so that there is significant overlap between two consecutive sigmas or distribution, not sigma, distribution. And I'll ask you why it is needed, but let me draw what do I mean by that first. So sigma should be selected such that the distribution has significant overlap, which means if this is my sigma 1, distribution corresponding to sigma 1, right? This is not sigma 1, this is distribution corresponding to sigma 1. Distribution corresponding to sigma 2 is probably like this. Distribution corresponding to sigma 3 is, and so on and so forth. This is what overlapping means. Okay, not exactly overlapping, but there is significant overlap. Why do you think it is needed? What is the problem if there is no overlap? For example, why not sigma like this is my sigma 1, distribution for sigma 1, and maybe the next one is something like, what is problem with this? That has nothing to do with independent, but something more practical. Think about the sampling. That's the clue. This is repeat. Why? How does it help? I mean, that is not 0, by the way, and these two will not act together. Remember that you are sampling from xt to xt plus 1. Maybe at xt you use sigma t, at xt plus 1 you use sigma t plus 1. So they are not acting together, right? So
It will be from the region.
yes.
The not overlap and that level will be.
Exactly. If it does not overlap, suppose let's take t and t plus 1. If t and t plus 1 does not overlap, so whatever sample you got in t, everything will get 0 probability in t plus 1. So the score will then become, again, the same problem that was there with manifold will come. So you do not want that every sample should have 0 probability in the next step. What you want is you select samples in annealing, in general annealing, and then you move those samples such that they have finite probability more or less in every step. Or even if they go to 0, they will go to 0 very slowly.
Yeah, only when doing this, so mean value.
Yes. So mean anyways is your x. So when it is the same sample, means will remain same. So in that sense, right? I mean,
The sigma is we are taking here are important. Some minus infinity to infinity, they will have a 0 actually.
that is theoretically. Practically, you go to minus 5 sigma, you will get 0. You don't want to be in the minus 5 sigma range or plus 5 sigma greater than that. You will not want that. Even if you take Gaussian, you will want this overlap to happen in minus, maybe within 1 sigma and 1 sigma. So 30% overlap should be there. 67% is, I think, 1 sigma plus minus sigma. So 33% overlap. Think about sampling. So at time xt, I have samples, right? So at xt, I have samples, I got it somehow. Now I'm computing score for xt plus 1. And those xt's I will substitute, right? What will happen to the score? Do you want that? That is the main problem. That's the problem. So when they are overlapping, at least most of them will have some finite score. No, that is not less. That is not true. That's what I said. Because they are not acting together. It's not reliability that you are calculating that what is the intersection. They are acting at different steps. You have to keep that in mind. So sigma t and sigma t plus 1 are not together. Sigma t is probably acting at time step t. Sigma t plus 1, that distribution will come at time step t plus 1. They are not acting together.
You are saying that score will be 0.
Is that so? I said probability will be 0. Probability will be 0. It's not score 0. Probability 0. That is also an issue, but probability being 0 is infinite and not close. That's the thing, right? Because this S theta, you can understand what a log of P of, well, P is be 0 there. So you are gone case, basically.
Same interpretation. There is a vacuum.
But there is no vacuum because you are looking at them together. They are not together. They are not acting at the same time step. When you look that kind of diagram last you saw in reliability, but that time they were acting on the same variable. Here they are not. No, at xt there is not two distributions. There is only one distribution. Why should there be two distributions at xt? Exactly. Exactly. There is nothing. Okay. So you understand why the overlap? Because otherwise the score will start creating issue. It will not be stable or whatever, right? Yes. So what are the things we discussed till now? Let us try to summarize. We discuss things here and there, but they're related. First thing we discussed is that with score-based model, there is a problem. And the problem is that many times the data resides on a manifold, and if it is manifold, the probability will become 0, log probability will become minus infinite, and that's a problem, right? That is what we discussed. So we said that can we not add noise to my data? But if we add noise to my data, the problem is that I'm learning accurately, but my target is wrong. And so we said that, okay, then let us add noise slowly. Initially higher and then slowly reduce it. And last step we'll have as minimum noise as possible. That we can do. But then for doing that, what is that big sigma and what is that small sigma? And what is the property of these different sigmas? We said that the big sigma, one of the way, and it's like a common sense answer, is that you take the maximum distance between maximum pairwise distance and take that as your sigma. This is a common sense kind of answer, right? Intuitive kind of answer. What about the small sigma? Ideally, the small sigma should be 0, the smallest sigma. But that's not possible because then the learning becomes very difficult and erratic. Okay, it will be a very small number. And let us decide it based on the problem at hand and training difficulty. If the training is not difficult, it is converging, let's take it 0 as well. That's also fine. Okay. The third one, we said, okay, but how are these sigmas to be scheduled? And we said the sigmas should be scheduled so that there is significant overlap between the distributions. Okay. And just to add one more thing, this distribution is Q of sigma distribution, right? This is not q of sigma given, or sorry, q of x prime, not q of x prime given x. Q of x prime given x will actually remain same. Not same, but same mean, and the variance will kind of increase. But this is q of sigma prime, the marginal distribution, and so you can see that shift because you'll integrate over x and all of those things, right? So that's why. Okay. Lastly, how will we get, who will give us this different s? Because remember, our s is trained for a given sigma. If I go back, score matching, this one, right? This is getting trained for a given sigma, right? But now we need scored network for different sigma, correct? So who will give us this network? How should we train our network so that it works for different sigma? One way is, if you have infinite resource, generate 100 sigmas that you want to take. For each of this sigma, you train your network. You have infinite resource, you can do that. And maybe the results will be the best in that case. But in real world, you will not have infinite resource, and that is not what you will be able to do. And anyways, that's not the intelligent way of handling things. What is the intelligent way of handling things? You will train a single network, right? But along with x, the input to that network should also be sigma. The output should be s, the score. So your input dimension will be k plus 1, output dimension will be k, because number of x and number of s should be same. So it becomes k plus 1, it remains k. So this is known as conditional denoising score matching or something like that. Okay. Obviously, conditional it is obvious. And then conditional denoising score matching. Okay, because you are conditioning on sigma and you are doing score matching. Okay. So you have some question? Very good question. Let us sample this. Let us sample this, but now with 10 sigma. How will you sample this? Let's start with x0. At x0, you will hit sigma 1. For sigma 1, you will get a scored network that is corresponds to only sigma 1. Right? Then in step 2, you will sample from sigma 2. For that, you need a second scored network which is corresponding to sigma 2. The same scored network is fixed for a given sigma. So you will need 10 scored networks for 10 sigma. Think about 1000 scored networks, 1000 sigmas, 1000 scored network. How will you train these 1000 scored networks? Separately. Who will give you those resources to train those separately? Right? That is why.
That's why we are just initially we are getting a single. How do we choose that input sigma value? Anything.
Input sigmas would be this one. That's what we were discussing, right? The highest ones would be the maximum distance, pairwise distance. The minimum ones would be very close to 0, and the intermediate ones will be such that the distribution overlaps. These are the 3 conditions. What else do you need to choose?
K plus 1. Input.
Correct.
Plus 1 will be our sigma value.
No. I am saying you want to sample from here. How will you sample? How will this work? How will this sampling work in annealing case? How does sampling starts? No, there is nothing training yet. How will you sample? For sample, you will need different S for different steps. How will you train those? You have to train those, right? You cannot train 1000 different networks. Let's train a conditional network where the network is conditional on sigma. So the question is, how to obtain the code network for annealing case. And the answer is you train a S theta, but S theta now will take x and sigma as input and will map it to S, which means it should work for different sigmas as well, right? Which means if I draw the network from last time, it was what, x1, x2, x3. Now the sigma is there, and then x1, s1, s2, s3. Sigma, and then s1, s3. Maybe this is the network connected. This is a S theta, right? Simple actually. What will be the loss function? Because now you need a loss function, and that loss function should be function of sigma as well. Sigma is sitting there. So
Issues we have that see
where?
when we do the denoising thing.
Oh yeah, that is there. But is that enough? Different sigma has to come into picture. So how will you do that? Simple. I will take a weighted average. Weighted average of different sigma cases. Right? I mean, basically the loss function will be f conditional denoising score matching theta is equal to 1 by L summation I equal to 1 to L. What is L? Let's see, sigma I, and then I'm writing here expectation x, it's x, right? Yeah, x from px, x tilde x prime from q, x prime x, and then what was inside? What was inside? It was grad of x log sigma I, no, log sigma, log q sigma I, sorry. Log q sigma I x tilde minus s theta x tilde comma sigma I norm of that, right? What have we done? Let us take a moment and understand. Suppose I have only one sigma, then L is equal to 1. L is the number of sigmas I have. So in that case, L is equal to 1, there is no summation, and let's say lambda of sigma is equal to 1. You see, I recover my original Fisher's divergence, right? So basically, what am I doing here? Think about it. What I am doing here is, I am calculating this Fisher divergence for each of the sigma and taking a weighted average of that. This is a Fisher divergence, nothing new, at least in the denoising score matching case. And then I am taking a weighted average of that for different lambdas, right? And not only that, this term, This term is my weight, obviously. And I am saying that this weight is my function of sigma. If sigma increases or reduces, this weight should not be same. Okay. Now for the Gaussian case, how will I change this? See, I can change it even more. What is x tilde? Can you tell me what is x tilde? X tilde, I can write it as x plus sigma I times z, where z is drawn from a Gaussian. Prime. Same here, right? Both are prime. So I can write x prime as that one, simple, and the other x prime also is the same thing. Correct. And now if I write the Gaussian form, what will I get? I mean, okay, there is one mistake, right? I mean, in the denominator, it will be log of x prime given x. It is log of x prime given x, right? So that the top one is correct, but the bottom one is wrong. This should have been the case, right? Only then it is Gaussian. So now if I write the Gaussian form, what will I get here? The log is there, so that will cancel out. Then the gradient is there. So ultimately we know that we will get x minus x prime, which is my z. So that term will give me my z by sigma square, right? And the other side is minus s theta. If I take sigma square up, then I will get sigma square s theta minus z prime. That's the same sigma. Same sigma. Okay. So what was the last thing I wrote? Yes. So which is equal to 1 by L summation I equal to 1 to L lambda sigma I expectation of with respect to x from P of x prime from Q of sigma I x prime given x, and then inside the norm I have, and now I'll write this gradient of log of that things, which is Gaussian, so it will be x minus x prime, right? So this is x minus x prime by sigma square, sigma I square, correct. This one, okay, let me write the total thing, minus s theta of x plus sigma I z. You can understand z is basically standard Gaussian sample. So now this is equal to z. So what I am getting here is z by sigma I square minus s theta of x plus sigma I. Something like this, right? Only the inside part I wrote. Okay. So something like this we will get. Okay. Now I wrote this part, there is a reason for that, because I will soon discuss what is a good lambda. So that lambda of sigma we need to select, right? The weighing factor. Because you need control over that not every loss will have equal weightage. Now, why is it important? Is probably the question you are trying to ask. Because if sigma is very small, that will have more weightage. Forget about that part, look into ins, because x minus x prime by sigma. Sigma being small, that term will, the target increases. If the target increases, so that overall loss will now be governed by that target. So what will happen is that your optimizer will only focus on that and not focus on the others. So you want that everything should be focused on almost equally. But that will not happen because of that sigma square being present there. Which means your weight should be higher when sigma square is higher. And it should be lower when sigma square is lower. So it is similar to, right? I mean, if you have 100 plus 1, 2 terms, and you need to reduce it, your optimizer will ignore the 1 term and maybe try to make 100 as 10. And you get the answer as 11. But ideally, both has to be minimized. Maybe 100 should come to 10, that's fine, but 1 should also come to 0.1. That you will never get in this setup. So because of that, that weight term is there.
Using the sigmas, typically you take any continuous function, right? Sometimes, like some fraction times the previous one, so that gives me like kind of, right?
No. You take it based on previous one, but we are not talking about that. What we are talking about is following. I have taken L number of sigmas. I'll get L number of loss functions if I write it in summation. Now this L loss function, if they are not in the same range, then what will happen is that your optimizer will focus on the highest range. If orders of difference is there, right? Now because of the sigma, there will be orders of difference. Because sigma is, let's say, 10 to the minus 3 and the denominator, it means 10 to the 3 in the numerator. So some terms will be in the order of 10 to the 3 and then some in the order of 0.1. This 0.1 terms will never be minimized. So your network will never learn how to predict score when sigma is high. So you need that weight for that. Okay. And for that, based on this discussion, suggest me a lambda of sigma I. Sigma I square. So based on this discussion just now, a good choice of lambda of sigma I is sigma I square. Okay. Because that automatically does when sigma is higher, the inside term is smaller, so this will bump it up. When this is smaller, inside term is higher, it will bring it down. Okay. Wait. This is equal to 1 option. I mean, again, you can decide your own, you can come up with your own idea of this. You can come up with your own good choice of lambda, and that's a perfectly good problem. But this is a reasonable choice, is what I'm saying. This is not the only choice. You can say why sigma is squared. It should be sigma to the power 4. I mean, decide it. It should, I mean, there can be many choices, right? But this is a reasonable choice because inside there is sigma squared, they will cancel out, and in some sense. So mostly no. That makes it unstable. Okay.
So what would be the major reason of that?
Which one?
Take this thing as a number.
Correct. So if you take it trainable, initially it might be possible that you are training. Remember, theta, how well you are training is depending on that. So initially the points, because of that points, theta can go anywhere. I mean, you don't know. Yes. It is highly possible because it will not know that its objective is to learn a good theta. It will try to minimize the loss. minimize the loss, the optimal lambda is 0. Make lambda 0, you will get the optimal loss, but that is not what you want. So the idea is that anything that is not function of your theta should not be trained. I mean, that becomes difficult. That becomes a hyperparameter, right? Clear? Okay. So this is how you train the network. Once you train the network, now you are ready for annealing. During the annealing, you find the upper limit, lower limit, overlap, number of steps, and based on that, you now sample. So what you are doing is basically this. Think about it. You will have some, let's say, signal. Let's take it as an image. And at starting, it is probably some noise, right? Then initially you are sampling for, let's say, sigma n. So what it will give you when you train it from noise and do the Langevin steps with the train network, this will probably give you some noisy version but less noise. This is noisy image or whatever. And then you keep on going like this. Ultimately, you will get sigma 1 or sigma 0, whatever you take it, I mean, last one. Probably the most clean image you can get. Right? This is one logical way. Some paper does this multiple times, but that you can decide, right? And you go to image and then again add noise and then again come back. That has also been tried. Okay. But this one makes sense, right? I mean, we're doing one step and you're keeping on adding noise and all of those things, right? I mean, not adding noise, but kind of denoising it. Just starting from noise and then removing the noise slowly, because your Q sigma, and obviously the idea is that okay, I have not written it once, so I should write it. The whole thing is based on this is the assumption we are anyways going with, right? I mean, in that sense, right? Now, those who knows diffusion will say that this is diffusion. It's not. Yes, so, and that is because of Langevin dynamics actually. So you need to change that sampler, but even then it's not diffusion actually, if you know. So remember what we have done here is that we have taken discrete number of steps, L, right? And each of that is a random variable or whatever in some sense, correct? The question is how many steps should we take? What do you think is the number of steps we should take? Theoretically. What do you say? Infinite. Theoretically, I should take as many steps as possible. If I take infinite steps, what happens to xt or this thing that changes? It becomes a random process because now it changes with continuously in time. Sigma t, let's call it sigma n and all those. Think of sigma t. Sigma t is now continuous in time, right? So whatever distribution sigma t is representing is a random process. When you do that, that's your diffusion. You extend it to make this thing process continuous. Ultimately, we will not do it continuously, we will use some discretization again, but at least the formulation is continuous. When that becomes continuous, that results in diffusion, which we will talk tomorrow. This is not diffusion, but this is very close to diffusion because you have done that you are starting from a noise and kind of denoising it in L number of steps. But mathematically, it's not because still there is no Ito calculus and SD is there, which will come now.
Also, you are not doing infinite.
Theory part is finite, infinite. And then you will discretize that theoretical part using Euler-Moriyama or something like that. Euler-Maruyama or Moriyama, whatever the pronunciation is. But anyways, okay. So this is conditional what? Noise condition score matching or something like that. I think that is the name. I forgot the name actually. I think it is noise condition score matching, but I'll check the name and confirm tomorrow. Okay. Any question? I mean, it is basically what we did last time, but with some more theoretical understanding of how things work, how sigma helps, why there can be a zero probability and why zero probability is a problem and so on and so forth. Right?
In the school network, minimizing would be still one step.
While training, it is one step. Training or sampling.
Sampling we are doing it.
Correct.
In the
Training, it's a single network. Single network.
not single. Minimizing would be one step.
Yes, but while training, remember that you are training this network, right? So there's a loss function. It's a usual training. There is no step here. Why should there be a step while training this?
During training also we
It's not, forget about it, it's not diffusion yet. So there is nothing to train here. Here all your data is there. You will, if you want to like, you think of L as steps. And then you can think that, okay, I'll first take for first one and then slowly do it. You can think of it like that. But it's not that. Everything is trained together. It's a one-go training. Okay.
Here it is necessary that it should be a decreasing one.
Yes. Yes. Because that's what we discussed at the beginning, right? When you're near the sample, it should be. Okay. Thank you.